In classical physics, energy is measured by its physical impact. It is macroscopic and tangible, relying on continuous fields that exert direct force to manipulate objects in space. This intuitive picture fails at the atomic scale. Here, matter resolves into probability wave functions rather than localized solid objects. This intersection identifies the core conflict. On the left, light travels as an electromagnetic wave, with fields oscillating continuously through space and time. On the right, matter is governed by quantum mechanics, restricted to discrete, quantized energy states. The classical framework attempts to bridge this gap through the Lorentz force, assuming that electric and magnetic fields physically push and pull charged particles along definite paths. Applying a macroscopic force to a microscopic probability cloud breaks the mathematical consistency of the Schrödinger equation. Because a quantum particle lacks a precise physical position, the concept of a directional push becomes inapplicable. Force requires the simultaneous knowledge of an object's position and velocity. Heisenberg's uncertainty principle proves that for an electron, these coordinates cannot coexist. Consequently, quantum mechanics replaces the concept of force with the Hamiltonian. Instead of tracking a physical trajectory, the Hamiltonian computes the system's total energy and determines the phase of the wave function. Classical mechanics computes an interaction by drawing straight vector lines of force acting against a localized mass. Quantum mechanics shifts the focus to how an environment warps and contours the quantum phase. To map this landscape, the Hamiltonian ignores the final electric and magnetic fields. It relies on the underlying scalar potential, phi, to define electric potential energy, and the vector potential, A, to define magnetic effects. Understanding the interaction of light and matter requires us to set aside the mechanics of physical pushes and look at how mathematical potentials directly sculpt the phase of quantum reality. The mathematical chassis for a free particle is simple. Total energy is determined strictly by its momentum and mass. We introduce an electromagnetic field by modifying the momentum operator, subtracting the vector potential multiplied by the charge, and adding scalar potential energy. This precise algebraic substitution is known as minimal coupling. In this coupled Hamiltonian, the particle's momentum is formally offset by the vector potential. This equation dictates that a charged particle is never mathematically isolated from its electromagnetic environment. The two are permanently bonded. When that environment is light, the potentials fluctuate over time. There is a massive scale disparity between a visible light wave, spanning hundreds of nanometers, and an atom, which is fractions of a single nanometer. Because the light wave is so large, its electric field remains uniform across the entire atom at any single instant. This allows for the electric dipole approximation, where light acts on the entire charge distribution simultaneously. This uniform shaking only causes a transition if the photon energy perfectly matches the gap between quantum states, promoting the electron to a higher energy level. Light absorption manifests as a precise rhythmic manipulation of an atom's internal potential landscape. This model introduces a mathematical complication, gauge freedom. Infinite variations of scalar and vector potentials can map to the exact same physical electric and magnetic fields. You can alter the potentials using an arbitrary function, represented here as chi, without changing the physical fields themselves. If the Schrödinger equation relies directly on these potentials, and the potentials can be changed arbitrarily, the physical predictions of the atom should theoretically fluctuate. Gauge invariance acts as the safeguard against this inconsistency. A wave function is defined by its observable magnitude, which determines probability, and its unobservable complex phase, represented here by the angle of the arrow. When potentials are altered, the wave function picks up a matching mathematical phase factor. This factor has a magnitude of exactly 1. It rotates the phase angle without impacting the size of the wave function itself. On the final dial, the arrow points in a new direction, but its length remains identical to the original. The observable probability is protected. Gauge invariance ensures that while our mathematical descriptions of potentials shift arbitrarily, the observable physical reality of the quantum system remains absolute. If gauge transformations rotate an unobservable phase, one might assume vector potentials are merely imaginary accounting tools. The Aharonov-Bohm effect provides the definitive evidence of their physical reality. In this experiment, an electron beam is split to pass around a shielded solenoid. In the region where the electrons travel, the magnetic field is strictly zero. Classically, this should result in zero physical effect. However, the non-zero vector potential A permeates the paths of the split electron wave packet. The detector screen records a physical shift in the interference pattern. This confirms a measurable phase shift occurred without any classical force, driven entirely by the vector potential. This shift proves that quantum particles are physically sensitive to electromagnetic potentials, validating a phase-driven model of reality over the classical model of force. The discovery that potentials drive quantum phase serves as the structural blueprint for modern applied physics. Minimal coupling governs everything from the magnetic spin transitions in MRI machines to the band gap excitations in solar cells and the stimulated emissions that power lasers. We have traced the path from the divide of classical fields to the bridge of minimal coupling and the mathematical protection provided by gauge invariance. This rigorous consistency allows for the extreme precision of modern technology. Mastering the interaction of light and matter is a study of how underlying fields sculpt the phase of reality itself.